Okay, so here's a very, very short breakdown of your weekend homework. I'm going to put the details up on Teams, so like pages, what you can do for review, whatever. So number one, you're going to do the exercises for 3.4a. We're going to go through 3.4a today. What the main bulk of the lesson is. You are going to study for your quiz on Monday, which is on particles and pure substances. You have that great big sheet on particles, but pure substances, there is no review material. You will need to review it on your own, okay? So, sometimes I don't have things for you and you just need to sort yourself out. And then finally, you should also be studying for your quiz on Tuesday, which is on average atomic mass. So yes, you will have to multitask this weekend. Spend maybe some of Saturday morning doing one of them, spend Saturday evening doing another thing, and maybe some of Sunday doing the third one or something like that, okay? So break up your time so you don't do it all at once. There you are. We are now going to go to, let's see, page 70. All right, page 70. Oh, by the way, your quiz, if you're unhappy with your mark, there is one rewrite. So make sure that you study before you do it. If you did one part of it wrong and you only want to redo that part, you may do so, but you would need to hand in your original quiz so I can take the 2 marks and combine them. Does that make sense? So if you did the chart perfectly and you just want to redo the bar models, that's fine, but you would need to hand in your original quiz so I can add the marks together. And there's how many rewrites on that one? Just one. Okay, so make sure that you have studied for it before you do a rewrite. All right, page 70. And the projector's not on. So everything I've been writing, oh my God, you had to tell me this earlier, because there was like a whole thing up here that told you what the homework was, but now it's not there. Okay. Okay, so your homework is there. Okay, so that's just what I told you about. I will put all of that on Teams. All right, so you can look at it and be like, yay, okay. It will all be on Teams. Page 70. You have previously learned the location of the metals and the non-metals on the periodic table. Please draw the staircase that separates them and then shade the non-metals. So you're drawing the staircase and then you're shading the non-metals. Take a moment and do that. So hopefully your staircase looks kind of like that. Should I be shading for the non-metals? Should I be shading to the right or to the left of that line? To the right. Unless you're like me. In my first block, I said to the left and then I shaded over here. It is to the right. Apparently I have a problem with left and right. Okay, so those are your non-metals. Have I missed any nonmetals? Hydrogen, don't forget hydrogen. Okay, there it is there. There is something missing from this periodic table. What is it? Yeah, that bottom part. Okay, so let's draw that in just so we can figure out if those are metals or nonmetals. And feel free to use your periodic table to help you with this, but I would like you to tell your neighbors what the name of those two rows are. Feel free to use your periodic table. No. Okay, so remember we have lanthanum and we have actinium. And so those two groups are the lanthanides and the actinides. Okay, so there we are. What, where? Come on, behave yourself, there we go. So these are the lanthanides. These are the actinides. And are these guys metals or are they non-metals? They are metals. Now what I would like you to do is once you've written that down, I would like you to flip your book over so you can no longer see this page. Okay? And then I would like you to discuss with the people near you what are some properties of metals and non-metals. So without looking at those, what are some properties of metals and non-metals? You might remember some from grade 8, 9, 10. You might remember some from just being alive in the world. Okay. So tell me something about metals. Anything. They are solid. Yes, they are solid. Who's the only one that's not a solid? Mercury. Yes. Now, what about nonmetals? Liquid or gas, or what's this? It's actually not lead, it is carbon. Okay, so this is what goes in my pencil. And is it solid, liquid, or gas? It is solid. Often people think the metals are solid, therefore the non-metals must be liquids and gases. But actually non-metals, some of them like carbon and sulfur and phosphorus, kind of the ones that are close to the dividing line, they tend to be solids. Okay, so you got your carbon, your sulfur, your phosphorus, iodine, selenium, those are all solids. Okay, then you have your gases, nitrogen, oxygen, and all your halogens other than iodine, and of course your noble gases are gases. So non-metals can be solids or liquids or gases. You should know by heart which metal is the one liquid. Which metal is the one liquid? Mercury. You should also know by heart which non-metal is the only liquid non-metal. Do you know that one? It's bromine. Okay? So if we pop on down here, you should know that bromine is a liquid, and you should know that mercury is a liquid. Hopefully you know metals are they shiny or are they dull? Metals are shiny, non-metals are dull. Okay? And what about the density? Which one is more dense? Which one feels heavier for its size, metals or non-metals? Metals. Like if you imagine, like, I mean, I know this is a small quantity, but even if you got a large quantity of graphite, which is this form of carbon, it would feel fairly light. Whereas if you had the same quantity of gold, it would feel fairly heavy. Okay. So for the density of metals is high, the density of nonmetals is low. Now, do you remember the word malleable? Have you heard that one before? What does it mean to be malleable? Like Play-Doh, except for metals aren't quite like Play-Doh, right? If I take it, I can't actually squish it, but what could I use to squish it? I could use a hammer. If I was to hammer on this piece of metal here, would it break? No, but it would deform, okay? That's why blacksmiths can hammer, metal into the shape of a horseshoe or a sword or armor or whatever, yes? So that is because metals are malleable. The opposite of malleable is brittle. So if I was to take my pencil lead, which is not lead but is actually carbon, what would happen if I hit it with a hammer? It would shatter into pieces, so brittle things will break if they are hammered. Ductile, anyone remember the word ductile? It's stretchable, okay? You can pull it into a wire. Now, I don't know how you like to remember it, but it made me laugh so much when I read this on someone's quiz last year. They said ductile, and then I told them they had to define the word ductile as well when they wrote it. They said metals are ductile, which means they're stretchable, like a duck. Like, okay, that made no sense, but I know this person and I know they're just being a goofball. Yes? And so anyway, that made me laugh a lot, and so I drew a little picture of a duck and then like a little haha. Anyway, it made me laugh, and I don't think I can ever forget ductile being stretchable, because now I have this picture of someone trying to stretch a duck, right? And the duck stretches, because I'm imagining like a rubber chicken or one of those things like that, except for it's a duck and now it's stretching. Okay, so those are ductile. Non-metals are non-stretchable, not like a duck. Okay. Metals are good conductors of heat. This is why all your pots and pans are made of metals. There was this weird period in the 1980s where they made like pots and pans out of glass, and they would hold the heat really well once they were warm, but it took forever if you wanted to boil your water, because it took so long for the heat to like move through the glass to make it to the water. So They were really thick, like it was like about this thick. So it was fairly strong, but still, I'm like, eh. Again, they were brittle, right? We do not, yeah. So, I mean, they were sort of like the kind of same kind of material as, you know, like a measuring cup, you know, that sort of heat resistant glass, but still not the best idea. There's a reason they're not really around anymore. And finally, that once we've stretched our duck into a wire, now it can conduct what? Electricity. Okay, so yes, it can conduct heat, but it can also conduct electricity. So your wires are made of, say, copper, for example. And in fact, you know what would be one of the best conductors to make your wires out of? Gold. Problem is, it's really expensive and it's very soft. So that could be a bit of a problem. Pardon me? Yeah. Any metal can conduct, but copper happens to be one of the very best ones. So for example, aluminum, they did use aluminum wires in, again, probably the 80s. And if you look where aluminum is, it is really close to the dividing line between metals and nonmetals. So as far as a conductor goes, it is not as good a conductor. So they tend to have a lot more friction within them when the current flows through, so it can actually be a fire hazard. So back when my husband and I were looking at houses, you had to watch out. If a house had been built in the 80s, you had to check and see if the wiring was aluminum, because if it was aluminum, that meant you had an expensive upgrade on your hands. So there we are. All right. So on the quiz on next Thursday, so Thursday, April 6th, Thursday, April 6th. So this is like 3 quizzes out. All right, you're responsible for memorizing that table, for knowing the identity of the 2 elements that are liquids at room temperature, and for knowing the definitions of the vocab words malleable, ductile, and brittle. And that would be in addition to the stuff from the first page of this, which is all your alkali metals, alkaline earth, transitions, halogens, noble gases, who are the main group elements, who are the transition elements, who are the lanthanides, who are the actinides. You should be able to label your periodic table by next Thursday. Okay? All right. There's one more thing that we need to know for that Thursday quiz, and that is on our next page, page 71. We are now looking at the metalloids. Can you guess what metalloids are? They're in between. They are in between the metals and the nonmetals on the periodic table. And it turns out that their properties are also in between the properties of metals and nonmetals. So for example, like a metal, they are shiny. They're conductive like a metal, but they are only so-so conductors. So they're not as good at conducting electricity as a metal, which is why we call them semiconductors. We don't actually call them so-so conductors, we call them semiconductors. And this is actually the only property of metalloids you are responsible for knowing. that is that they are semiconductors. The reason that I'm making you know that one is because it is the fact that silicon, which is a metalloid, is a semiconductor that you have phones that work, that you have computers that work, that you have, you know, a stove that has anything more that like you can actually program it. Anything that involves any kind of programming, anything that has programmable hardware is due to the element silicon and some of the other semiconductive metals, and it is their semiconductive properties that allow them to do that. Back in the 2000s, there was a huge technology boom. Did you guys ever hear about that? Okay, huge technology boom. There was, have you heard of Silicon Valley? Okay, Silicon Valley down near San Francisco in California, big technology center, okay? So, and everyone was making money hand over fist, like everyone had a startup company and they were all doing all sorts of things. In fact, my husband belonged to a company that was up here and they were making money like crazy. And on paper, for a while, probably around 2006, we had lots of money. But my husband was like, oh, our investments, we should diversify. So being young and, you know, not knowing a lot, he diversified into other tech stocks. And then in 2008, tech stocks all did this. So on paper, for a while, we had lots of money, and then we just had a normal amount of money like, you know, everybody else, which was fine, right? Because I had a job and he had a job. It wasn't like we were not earning money. We just weren't rich anymore, darn it. But anyway, that's okay. So semiconductors made all of that possible. All right, without semiconductors, we couldn't do any of that. So I feel like it is important to know that metalloids are semiconductors. The other ones, I don't really care as long as you know that they're sort of like metals and they're sort of like non-metals. They're shiny like metals, but they are brittle like non-metals. I should write like non-metals. Okay, they are typically solid at room temperature, but you know that metals are solids and non-metals are also solids. And if you look at the position of the non-metals that are solids, you see the yellow ones? Those are our solid non-metals. And then I'm going to put our metalloids they're all the non-metals that are solids are right beside the metalloids. Yeah? Now you don't have to color that because on our next page, there's actually a place for it. So don't worry about that. The metalloids are solid at room temperature, and they tend to form covalent bonds, and that is like non-metals. Okay, so they tend to form covalent bond like non-metals. So they're all the ones that border the staircase except for aluminum. So they're the ones that touch the staircase. So you can see boron touches the staircase, silicon touches the staircase, not like a diagonal touch, but like a literal, like shares a border with. The only one that doesn't fit that pattern is aluminum. Aluminum touches the staircase, but it is a metal, not a metalloid. But all the other ones, silicon touches the staircase, germanium touches the staircase, so do arsenic and antimony, tellurium, and polonium. And then you might get down to the bottom here and you might think, what's going on at the bottom, down at the bottom right here? There are no shading, there's no staircase. What is happening, Ms. Spence? Well, it turns out down in this corner, the elements are very radioactive and they are very unstable. Therefore, they are hard to study. So do we know much about their properties? Not a whole lot. So it's really hard to say. Is whatever LV is or TS or OG, are they shiny? I don't know, because they don't stick around long enough. And even if we could study them and find their properties, this is grade 11 chemistry, and we deal with mostly just the common things, okay? So we don't need to worry about that bottom right-hand corner. We're only in grade 11, we don't care, okay? That's what it comes down to. You're not expected to know anything about those ones down at the bottom. So just don't worry about it. If all you want to write there is just don't worry about them, that's good too. Okay, so that, I think, is it for the periodic table. Yes. Okay, so part of your homework is going to be 3.4a. That's this worksheet. It will help you review for Thursday's quiz. Right now, though, we are going to move on to 3.4b, which is on page 74. And you are going to try and fill in the boxes and fill in the blanks to the best of your ability. Yep. And then you are going to, and then we're going to go over it together. Those of you who are on your phones should get off your phones. Page 74. You don't have to fill anything in up here. This is just showing you that we're only looking at part of the periodic table, okay? Just fill in these boxes like here. Pardon me? Yeah, it's all the electrons that are not in the outer shell. Okay, so core electrons are all the electrons that are not in the outer shell. That's probably a new concept. The valence electrons, if you want to get very specific about it, they are electrons in a partially filled outer shell. And that has a consequence for how many valence electrons there are for the noble gases. Noble gases, what can you say about their outer shell? It's all full. It's not partially full, it's completely full. So how many valence electrons do we have in the noble gases? 0. There's only the electrons that are in a partially filled outer shell. So let's go through how many shells in period number 1. Oh, by the way, I should have said, the rows are called periods, and the columns are called groups. How many shells are in row number 1, period number 1? 1. How about in period number 2? 2. How about in period number 3? 3. And I didn't have room to write it, but we could throw it in over here. How many shells in period number 4? 4 shells. Excellent. Okay. Now, talking in terms of, we're now going to look at groups. How many valence electrons are there in group number 1? 1 valence electron. How many valence electrons in group number 2? 2 valence electrons. And then you'll notice we skip over all the transition metals, okay? We can't do anything with them in terms of their valence electrons. How many valence electrons in group 13? 3, and then we have 4, 5, 6, 7 is where the halogens are. And we're also going to, I'm going to get you to think about this one. How many core electrons are there in period 1? How many core electrons? Tell your partner what you think. How many? 0. Because there is nothing that's not in the outer shell. It's all outer shell. There's only one shell. How many core electrons are there in period number 2? 2. Okay. Everywhere we look, we're like, oh, look, there's 2 of them here. There's 2 of them here. All the way across, there are 2 core electrons. How many core electrons in period 3? There are 10, 2 on the inner shell, and then 8 on the second shell. So 2 plus 8 is 10. And then finally, in period 4, how many core electrons? 18, because we had those 10, and then we add another 8, so there are 18 core electrons. All right, 3.4c. We're going to be moving out of the realm of Bohr models and going to the simplified form of Lewis dot structures. Lewis dot structures are simplified versions of the Bohr model, and they include only the valence electrons. And actually, not the valence electrons, but the valence shell electrons, and that will become an important distinction when we get to the noble gases. They are also known as Lewis structures, Lewis dot structures, electron dot structures, and electron dot diagrams. I will probably refer to them either as Lewis structures or Lewis dot structures, but you might see any one of these terms. So how do we go about turning a Bohr model into a Lewis dot diagram? Well, first of all, we need to have our Bohr model. This is nitrogen. And nitrogen is atomic number 7. Therefore, what does that tell us about nitrogen? A nitrogen atom has 7 protons And it also tells us that it has, not necessarily 7 neutrons, but it has 7 electrons. The number of neutrons is going to depend on the mass, okay? But we know we have 7 protons, we know we have 7 electrons, and the electrons go 2 in the first shell, and then 1, 2, 3, 4, 5 in the second shell. First thing we do is we get rid of the middle bit, because we don't, when we're doing a Lewis structure, we only care about the electrons, not the protons and neutrons. So we're just going to put an N in the middle, representing nitrogen. The next thing we do is we say, I don't care about the core electrons because they are not involved in bonding. And when we're doing Lewis structures, we're mostly looking at how things bond with one another, and only the valence electrons are involved in bonding. The other shells are full, so they're stable, so they don't need to bond in order to become stable. So it's really only those valence electrons. And then we say, well, gosh, if I've simplified it that far, why don't I just get rid of the circle and move all those dots closer to the center? So you put in 1, 2, 3, 4, 5, just like we did on the outer shell of nitrogen. Now, to be honest with you, it does not matter where this pair goes as opposed to the singletons. Okay, you see how you have unpaired electrons here, here, and here, and then we have a pair on the top. It really doesn't matter which ones we draw where. So for example, it would be fine to draw nitrogen with the paired electrons on the top, the paired electrons on the side, on the other side, on the bottom. It doesn't really matter. Each and every one of these are correct. Okay? Now, if I said to you, please draw me the Lewis structure of oxygen, you probably don't want to go through this whole process to get to the end, because you might as well be drawing Bohr models if that's the case. But the nice thing is you only need to know the number of valence electrons to draw the Lewis structure. So if we go to our periodic table, and we look at oxygen, here is oxygen. What group is it in? 16. Therefore, what do we know about it? It has 6 valence electrons. Excellent. Okay, so oxygen has 6 valence electrons, and so we can write O, and then we can do just like we did for the Bohr model. We'll start with one at 12 o'clock, and then we'll put our second one at 3 o'clock, and then our third one at 6 o'clock, our fourth one at 9 o'clock. So we go top, right, bottom, left, and that's 4, and then we'll add our 5th one and our 6th one. And that is the Lewis structure for oxygen. Is good? Okay. In a Lewis structure, we are drawing the electrons in the valence shell, which is slightly different from the valence electrons. Electrons in the valence shell just means they are the electrons in the outer shell. Okay? And valence electrons only refers to electrons in a partially filled outer shell. This mostly doesn't matter except for when it comes to the noble gases, because if I said, how many valence electrons do the noble gases have, you would say 0. But when we are drawing a Lewis structure, we are going to draw all the electrons that are in the outer shell. So neon, for example, has 8 electrons in its valence shell, and so we would draw 1, 2, 3, 4, 5, 6, 7, 8, and that would be the Lewis dot structure for neon. In fact, all the noble gases and I'm going to put an exception here. We'll fill it in a moment. Have 8 electrons in the valence shell. So it doesn't matter which one you have. You could have xenon, 1, 2, 3, 4, 5, 6, 7, 8. You could have radon, 1, 2, 3, 4, 5, 6, 7, 8. They're all going to have 8 electrons in their valence shell. Who is the one noble gas that will not have 8 electrons in its valence shell? Helium, yes. And that's because helium, we're filling up shell number 1, and shell number 1 is full with 2 electrons. Now here's a question for you. Should I draw helium like this, or should I draw helium like this? Which one? Let's think about the Bohr model of helium. Yes? The first two get paired because there's only one orbital in shell number 1. So this one is not correct. This one is correct. That's going to be different than if we were to do beryllium. Let's do the Lewis structure for beryllium. So first of all, how many dots will we want to go on that structure? 2, because it is in group 2, okay? So now the question is, for beryllium, should it go like this, or should it go like this? The first one. And the reason is that now we're no longer showing the first shell, which is full with 2. This is actually the second shell of beryllium. And one of the electrons goes here, and one of the electrons goes here. Remember, electrons do not pair up until they have to, okay? Okay. So there's going to be some practice here for you to do. We'll do that next week. Now, let's review for ourselves here. Out of all the various colors, which ones are the main group elements? Who are the main group elements? Yes, they are yellow. Okay, these ones here. If you have a highlighter, you can highlight it for yourself. These ones over here. And the nice thing about these ones is even once we get past calcium, what happens at calcium with Bohr models? After calcium, Bohr models, they collapse, falls apart, doesn't work, okay? But Lewis structures don't work the same way because valence electrons don't work the same way either. Valence electrons are predictable for all of the main group elements, not just up to calcium. All the main group elements, they all have a predictable number of valence electrons. So for example, let's say that we went to antimony, which is Sb in some completely illogical fashion. Okay, antimony is Sb. What group is that? That is group 15, just like nitrogen. You remember we did nitrogen earlier? How many valence electrons did nitrogen have? Group 15, 5. Okay, so how many valence electrons does antimony have? 5. Okay, so this entire group here has 5 valence electrons. So if I were to draw the Lewis structure for antimony, even though it's way down on the periodic table and the Bohr model has fallen apart, it still has 5 valence electrons, and its Lewis structure would look exactly like that of nitrogen in the same group. In fact, if I was to give you phosphorus, which is also in that same group, what would it look like? 1, 2, 3, 4, 5. So everything in the same group all looks the same. They all have the same number of valence electrons. So if you can draw a Lewis structure for oxygen, you can draw the Lewis structure for sulfur and selenium and tellurium and polonium because they will all be the same. Is good? Okay. And in fact, it says that here, all the elements in the same group will have the same pattern of dots because they all have the same number of valence electrons. And now for something completely different. We are going to take a little divergent thing here. This is actually on, you don't even need to have this in front of you, but it is 3.1F, which is on page 25 if you are interested. It is a video, okay, on the quantum mechanical model, because I keep telling you that the Bohr model falls apart and that I've talked about these things called orbitals, and so far we've drawn little boxes. You are not meant to understand anything that goes on in this video. You are not expected to know anything that goes on in this video, but you are expected to get a flavor and a feeling for the fact that life is much more complicated than the Bohr model or the Lewis structure. Does that make sense? Okay, so it's Friday afternoon. You can sit back, relax, and be like, this is going to be some weird stuff, okay? All right, so here we go. Get that up and running. hope it comes up and running. Waiting for it to be big.
Quantum mechanics and the shape of atoms as discovered by Schrödinger.
No. Just chill, okay? There we go. Let's make it bigger. Oh, Lordy. Hello? Why can I not make it bigger? What is wrong with it? Ah! Okay, let's see if I can make it smaller. There we go. Now let's try making it bigger again. See if it works this time. This time it works. Excellent. Okay, here we go. And if you have your phone out, you're going to miss some awesome stuff. So put your phone away.
Quantum mechanics and the shape of atoms as discovered by Schrödinger. We all know about quantum mechanics, which is of course the physics theory that describes atoms and elementary particles, how they move around like slushy little waves, and...
By the way, it really annoys me that he has C capital L and then F capital E and B capital A. Yes? Yeah. Like, he should have lowercase letters. Yes. Anyway.
And interestingly, it predicts what they look like, what shape they have. It was invented in the first couple of decades of the 20th century by a lot of people all working together. Amongst them were Planck, Heisenberg, Bohr, Davison, Du Broglie, Einstein, and of course Schrödinger.
You remember how I said Heisenberg was a scientist? He was a scientist back in the early 20th century.
These guys already knew a lot about atoms from the scientists who came before them. For instance, they knew that there are about 100 different atoms in nature, and that these atoms join in larger structures such as molecules, metal lattices, and salt lattices to make everything we see around us. But what they didn't know, what exactly was going on the inside of the atom, what it was made of, what shape it has. So they were doing experiments on that. And pretty soon they found out that atoms themselves are composed of smaller particles. They found the proton and the electron, and they were theorizing the neutron. And with the protons and neutrons, they almost immediately knew what the deal was. They realized that they were clumped in a very tiny core at the center of the atom. That core was really small. A typical atom is about 300 picometers across, whereas that core is typically 0.01 picometers.
Is 1,000 times smaller than a nanometer. So nanometers are 10 to the negative 9 meters. Picometers are 10 to the negative 12 meters. So about a trillionth of a meter.
So this leaves this big open space in an atom. And they realized that this open space was going to be the domain of the electron. But what they didn't know was exactly how the electrons are filling this space. If they are spinning around or orbiting or what. So they made an initial sketch. They called it the planetary model of the atom. Basically the core at the center and the electrons spinning around in big orbits. It was their first idea of what an atom looks like. It proved to be incorrect, but it was a fine enough starting point. It made some very nice predictions, and it allowed them to start doing experiments.
This was the model that Bohr is sort of built on. Bohr built up on this and said that you can't have them at any distance from the nucleus. They're only at very specific distances. Okay, so in a specific shell, but he was still thinking planetary model.
And they did. One man who was looking at these experiments was a Frenchman called Du Broglie, and he was noticing something very interesting. He found that when the electrons were forced to interact with matter, either through some physical process or by hitting a detector, that the electrons presented themselves as particles, as hard little balls of matter.
And that's kind of what you would expect, isn't it? An electron, it's a little ball of matter. Yes, a particle. Sounds good, yes? Okay, but it does get weird now.
Kind of what you expect them to do. But when the electrons were allowed to move on their own, either by being shot through a crystal or allowed to wander through a vacuum, they always propagated as if they were waves. It was almost as if when you stopped messing around with the electron, it would suddenly fall apart into some sort of wave function, some sort of probability wave that sloshed around all of space and predicted where the electron was likely next to be found.
Okay, so we're thinking electron, nice little ball of matter. That makes sense to my little human brain. Yes, there's an electron. Okay, except for if you stop looking at it, it becomes a probability field. It becomes a wave. It becomes an area in which you are likely to find that particle if you actually interact with it and look at it. So this is what it's like when you're looking at it. This is what it's like when you're not looking at it. Isn't that fun?
This was the first time they encountered particle-wave duality in matter, and it spelled disaster for their planetary model. Because this model really assumed that the electron stays a particle during the entire orbit and doesn't fall apart into a wave halfway through. So, they needed a new model, but they realized that this model couldn't come from classical mechanics, because classical mechanics makes the same assumption that particles stay particles. In fact, they would need entire new mechanics, some new theory that included the wave-like nature of particles. And this is when Schrödinger entered the picture. He had looked at the experiments as well, and he found one common theme running through all of them. In his insight, he saw one law of nature, one equation that seemed to hold no matter what you did. He called it the wave equation.
Now, that was in my first year university chemistry textbook, and it absolutely scared the snot out of me. Yes. Yep.
Nowadays, we simply know it as the Schrödinger equation because it was the rock-solid core onto which all of quantum mechanics was built. Schrödinger realized that with this equation he was now in a very interesting position. What he could do is take an atom, any atom, take its properties, stuff like its mass and its charge, all those numbers.
Hydrogen, for example, the simplest of all atoms. He's going to take the mass and the charge and various other things, and now he's going to do some math with it. Okay, remember, this is the simplest of all the atoms, and he's going to show us the math that they did with it.
Put that in that equation, do the math on it, and what he would end up with would be a series of pictures that showed what that atom looks like. He went on and did it for hydrogen, which is the easiest atom, it's just one proton, one electron, and that one proved to be crucial into unlocking the shapes of all the other atoms. And when he had worked his way through the math, these are the pictures he found. Ladies and gentlemen, the shapes of hydrogen. So this then is how an electron fills the empty space in an atom, not by spinning around, but instead with its blobby-shaped wave function.
So, when we drew those little boxes on our Bohr diagrams and said this is an orbital, they aren't really boxes. They really look like that, or that, or that, or that, or that, or any of these. Okay, that's what orbitals really look like. They aren't boxes, they're blobs, blobby shapes.
Which we call the orbital. What I've drawn here each time is just the same hydrogen atom with a proton at the center, and the electron has been allowed to go into a different orbital each time by giving it energy, for instance. And if you look at this one, these three blobs together form that one orbital. They house that one single electron. And this one makes a fine example. We can look a bit at its properties. What you can do in an experiment is take a hydrogen atom and prepare it in this orbital by giving it some energy, for instance. And if you leave it undisturbed, then the electron takes this shape. It becomes this wave function, this blobby shape.
Okay, so if you're not looking at it, if you're not interacting with it, the electron is not a little ball. It is that shape. Okay? I know that's weird. Just go with it.
And if you then were to take a measurement of the electron, find out where it actually is, what would happen is this wave function suddenly collapses. It condenses into a single point, which we call the electron.
So, when you interact with it, it ceases to be this big blobby shape, weird blobby shape, and it becomes a single little tiny particle like what we would expect an electron to look like. And that electron will be somewhere within that original blobby shape.
If you then were to re-prepare your hydrogen atom in the same orbital, maybe give it some new energy, then you can do a new measurement, and you can find that electron in the same blob, or in any of the other blobs. And if you were to repeat this thousands of times, you would end up with a picture very much like this.
So every time you do the experiment, the electron will be in some different place. Okay?
Notice that there's a high probability of encountering the electron at the center of a blob. There the probability wave function becomes more dense.
Okay, so what he's saying is that the chances of finding the electron in the center of the blob are quite high, whereas the chances of finding the electron in the outer part of the blob are much lower. Okay, same thing, there's a high probability of finding the electron in the center of this ring, but not towards the outer edges of the donut. Okay?
But there's something interesting about these pictures, of course, something that is, well, staring us in the face. The fact that these blobs are not connected. There's an area in between where you cannot encounter the electron. So it kind of begs the question, how on earth is the electron traveling from one blob to another? Is it teleporting or what?
Yes. So the electron, it could be here or it could be here, and at one moment it might be here and then it might be there, but it's never in between. Okay? So it might be here 1 minute and there the next minute, but it never actually is in the space in between the two blobs.
This was one of the important questions that led to 40 years of heated debate that ended up with Einstein saying very angry things about dyes. But
so, here's the moral of the story. Einstein did not like this. He did not feel comfortable with it. So there is no way that me, with my poor little human brain, is ever going to feel extremely comfortable with this idea. Never. I'm never going to understand it. I have no hope of understanding it. I have come to terms with this idea. I have come to terms with the idea that it's a blob. Then it's a particle. It's a wave. It's a probability field. And then it's a particle. So if you look at it, it's a particle. But if you're not looking at it, it's kind of like a blobby wave. Okay? And in my brain, I'm kind of okay with that. But like if I really start to think about it, I'm not actually okay with it. Right? Because I don't know what that means. I don't know how it happens. And I never will.
But who cares? Schrödinger had made an important discovery. He had found the shapes of hydrogen. And using that as a basis, those that came after him were able to find the shapes of all the other atoms. They are very much based on hydrogen. They use the same orbitals. It's just that the higher atoms consist of more electrons, therefore they require more orbitals to house all of them. So you end up with a situation where the orbitals all get stacked on top of one another, overlapping but not mixing. They do, however, repel, because that's what the electrons do, they repel one another. So the orbitals begin distorting each other according to some very complicated math, but these guys were also good at what they were doing. And, combined with Schrödinger's discovery, they had now made a link between physics and chemistry. A link which in fact led to an entire revolution in both of them.
Okay, and so due to quantum mechanics, we could have molecular design, MRI scanners, electron microscopes, string theory, transistors, microchips, intercellular molecular spectroscopy, all sorts of things that could not exist, diodes, which includes LEDs, light-emitting diodes. You could not have any of this without quantum mechanics.
So with that, I would like to conclude by just saying, Mr. Schrödinger, thank you very much.
So, you need to know nothing of that. Where will your homework be? On Teams, okay? If you remember nothing else, you need to do 3.4a and study for your 2 quizzes. Yeah. Yeah. Okay. Do you want to take this with you and a blank copy so you can practice? Yeah? Okay, cool. Let me find a blank copy. Well, I will, but you'll bring it back to me. You won't lose it, right? No. See, there you go. Okay, now what have I done with my blank copies? This is a fine question. Why did I take everything out of the drawers? Oh, that's right, because I couldn't find something. So I took everything out of the drawers, and now I'm really regretting that decision. No, that's the requiz. But the non-requiz should be somewhere here. Let's see. Quiz. There you go, and there's your original. Hi. Yes, you can. Yeah.
And then, sorry, do you mind if I ask a question about the video there?
Of course.
So you say that when you're not looking at it, it's all that kind of like mess, but when you're looking at it, it's like
Particle. Yeah.
So is it like to us it looks like that, but like it's actually that, or is it like that inside something? Like how would you kind of?
What it means is when, in order to see it, and when I say see it, that's going to be a quote, small to see.
Right.
Okay. But if you hit it with something like another particle, it will bounce like a particle, and that will tell you where it is, because you'll be like, oh look, it was there, and then it hit something.
Okay.
Okay. But if you let me see if I have a picture of this. And I'm sorry about this. This was their drawer, and I'm just like sort of halfway. I'm trying to clean it up, but I haven't had any time all day. Anyway, let's see, particle wave duality. That would be at the beginning of chapter 6. See if they have it here. 7, 6. Hi.
Yeah, I know it's 1 minute before the bomber. Can I use the washroom?
Yes,
I don't
you may
like
use
it
the
when it's
washroom. Yes,
crowded.
it's fine. They don't have it here. That sucks. But there's like an experiment that they do where they're like, you shoot an electron through. That'll do. You shoot an electron through a double slit like this, like you sort of have electrons going like this. And if they traveled like particles, you would expect them to, go straight through. Yeah? But they don't. What happens is you end up seeing a pattern that looks like this. Bye. And you see actual interference. And that's the pattern you would get like with a wave. Like if you see a wave in a pool, it's like, right? And that's what you end up seeing. It travels through a slit.
That's really interesting. Though I like that. I like seeing that. Yeah. So,
right?
So to us, it's like a particle, but once you hit it with something else, it kind of reveals what it like actually looks like.
No, when you hit it with something else, it looks like a particle.
Right.
When you just leave it alone, that's what it actually is. Yeah, it's a wave, like not doing anything.
So leaving it by itself is kind of like its raw form, and then something else is kind of.
And then it kind of condenses into a particle.
And that's what we usually see, right? Or
yeah. Well, that's the only way we can.
I guess.
Yeah. Although, yeah, that's how you can be like, okay, where is this electron? I'll do something with it. I will find it. But it's not really just there all the rest of the time. All the rest of the time, it's everywhere within that blob. It is that blob.
Right.
Yeah.
That's really cool. I really like that.
It is really cool. I'm gonna see if I can find some other. Like, I know there's a couple of really good PDFs stuff on like quantum mechanics, and you'd probably really enjoy it. Like, if you like that, you'll probably like the other stuff too. There's like weird things. Spooky action at a distance. Look that one up. Spooky action at a distance. Yeah.
I like to see that. Yeah.
Yeah.
Pretty cool.
Yeah. Hello, hello.
Are you still being recorded right now?
Probably.